So, the program says it is for 3 dimensional analysis. Input will be the number of members 3, EI is taken as 1 for the time being. We said EIY and EIZ are EI. We also said the torsional constant GIX, okay, is 1/4 of EI. EAX is also 1/4 of EI. Length of the member is 3, we have input. Number of joints will be number of members plus 1. Let us also work out the coordinate matrix of all the members. We already have it here, you can see here 0 0 0, 3 0 0, 3 0 3, minus 3 and 3 minus 3 3. We input that here. We can see here, okay, we can input this. Then direction cosines we just now worked out, we already have it here, see here 1 0 0, 0 0 1, 0 0 minus 1, 0 1 0. Let us look at here 1 0 0 0 0 minus 1 and 0 1 0, okay. So, no issue. Then let us try to find out the type of transformation. 1 corresponds to, in this 1 corresponds to y z x transformation and 2 corresponds to z y x transformation. We know for members 1 and 2 it is y z x, for the member 3 it is z y x. So, we said 1 1 2, okay. Psi angle we computed 0 0 and 90, you can see here 0 0 and 90, we input that 0 0 and 90. Now, we now form the C matrix for member 1, 2 and 3, okay. Just now we derived this, I will show you for C 1 1 0 0, 0 1 0, 0 0 1, you can see that here, just now we did that C 1. Similarly, C 2 and C 3 we input that here C 1, C 2, C 3. Number of understand degrees are 12, restand degrees are again 12. The global label for understand degree you can see here, it varies from understand degrees 1 to 12, restand degrees 13 to 24, sorry. So, 13 to 24, 1 to 12, okay. Now, the global labels for member 1 13, 14, 13 to 18, then 1 to 6, see here global labels 13 to 18, then 1 to 6, we did the same thing exactly here, okay. Then for member 2 1 to 12 continuous, for member 2 1 to 12 continuous, then for member 3 19 to 24, then 7 to 12, for member 3 19 to 24, then 7 to 12, okay. We entered that. Then we formed the degrees of freedom, then we found out the fixed end moments. You know, the fixed end moments are going to be computed based on the loading. The loading on the member is only on the member AB. So, the member AB will have moments and the fixed end moments can be simply said as only on the member AB. Member AB, the member has 13 to 6 as the degrees of freedom. So, I can write down here is the fixed end moments of the member AB on labels 13, 14, 15, 16, 17, 18, then 1, 2, 3, 4, 5, 6. So, 13 is along x, so no force, okay, so no force. 14 is along y, there will be a reaction. The total load applied is 20 into 360. So, 30 this way and 30 up way. So, plus 30 along z no force, about x no force, about y no force, but about z there is going to be reaction moment end moment W L square by 12. So, W L square by 12 which will be 20 into 3 square by 12, okay, which amounts to 15. So, plus 15 along 1 along x 0, along y again plus 30, along z 0, about x 0, about y 0 and this is going to be minus 15. The members BC and CD, see there are no loads in BC and CD, therefore, the fixed end moments along BC and CD will be 0. Okay. Now, I assemble this and get the joint load vector. So, we have entered 0, 30, 0, 0, 0. So, we can check here 0, okay, 30, 0, then 3 zeros up to 30, then plus 15, 1 0, plus 30, 2 zeros, 3 zeros and minus 15. Remaining other members are 0 and 0. Then continue the coding. We then form the transformation matrix, then we find the stiffness coefficients which we derived in the previous lecture for the entire matrix. We get now the stiffness coefficients and stiffness matrix for the member AB, for the member BC, for the member CD. Then we find K global of the member AB, which can be T transpose K T of the member K bar BC, then K bar CD now can be computed. We assemble this to get K total. In that we partition unrestrained degrees and restrained degrees separately, and I can get K U U. Okay, that is what we are doing here. So, K local stiffness matrix, then we said K global, that is T transpose K T, then global stiffness matrix for all the 3 members, then complete stiffness matrix, then from that unrestrained stiffness matrix and inverse of that. So, we get K U U and K U U inverse from these 2 steps. Okay. After that we create the joint load vector. Okay. Joint load vector is nothing but reversal of FEM vector. We create that vector, then we found solve for del u. Okay. Del u is nothing but K U U inverse of J L U, all are in reference axis system. I get delta u bar. Once I get that, I get the member forces, okay, in global displacements. Let us look at the 3 members, then ultimately the joint forces and check for this, that is the program. Let us look at the output. Member 1 y z x and psi angle 0, you can see here member 1 we are going for y z x psi angle 0. Okay. Similarly, member 2 and member 3. So, that is my local stiffness matrix for member 1 and K bar for member 1. You know the stiffness, the rotation matrix for member 1 is identity. Okay. Therefore, you get exactly K local and K global for the member 1 as same. Okay. So, I get K bar A B now. Then I find K local for the member 2 and K global for the member 2. So, I get K bar B C now. Then I get K local for the member 3, I get K global for the member 3. So, I get K bar C D now. We have EI multiplier in all the cases. I have an EI multiplier in all the cases. Please understand that EI is taken as unity in this case, okay, EI multiplier. Then we find the full stiffness matrix, okay, the full stiffness matrix, which is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 and 24 by 24. Full stiffness matrix we got, out of which at 12 first, second, third, 4, 5, 6, 7, 8, 9, 10, 12. So, I have to will be partitioned here, is it not, to get SUU and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, another partition here, correct. So, this may unrestrained degree, this may restrained degree, this may unrestrained degree, this may restrained degree. So, KUU will be actually this block, the left corner, I get KUU, I get KUU which is exactly same what we have here. I can check that starting from 0.5278 ends at 1.4167, 1.4167, 0.5278, which is going to be 12 by 12, you can see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. I take the inverse of this. So, I will get a multiplier k u u inverse, I get 1 by E I, here there will be E I out, this is k u u, okay. I get inverse. Once I get this, I have my joint load vector, okay. I get my delta u bar as this value, okay. Then I substitute, run the program, get the global values of member 1, member 2, member 3 and the end reactions in the entire structure by assembling these 3, which I want to plot and show you. So, let us do it for member wise. First member, second member and let us say third member. If you look at the first member, this is the first member minus 0.04. So, you can see here very clearly this along these 3 will be translation along xyz at jth joint. This is the next 3 will be rotation about xyz at jth. So, this is about jth and this is about kth and this 3 will be translation, this 3 will be rotation along xyz respectively. Let us mark them. So, minus 0.051 means negative, okay. Let us mark it here, let us mark that here 0.0451, okay. And along y you can see here along y 55.7251. So, 55.7251 and along z. So, negative, see here along z is negative minus 1.543. So, 1.543, that is about the translation. Let us mark the rotations. So, the first 3 values are now done, the next 3 values will be done, then the next 3, then the next 3. So, this is for the jth n and this is for the kth n, correct. So, minus 2.82. So, minus, how to get that? Put your thumb towards this arrow, the remaining 4 fingers will give you the rotation, minus means it is opposite, okay. It should be opposite. So, it should be clockwise 2.82. Similarly, 73.23 and similarly 4.356. Look at this joint now, this is going to be 0.045, okay, and this is going to be 1.543 and this is going to be 4.275 and then the rotations clockwise, this is anti-clockwise 2.82, 0.284, 0.284 and this is 3.943 for the member AB. Let us do for the member BC. This is 1.543, okay, and this is down 4.275 and this is this way 0.045 and then the moments, this is 2.82, this is 0.285 and this is 3.943 and for this joint is going to be 0.045 0.45, 4.275, 1.543, then 10.004, 0.42, 3.943. Let us come to this 0.045, 4.275 and 1.543, then 5.374, 0.42, 3.807, 4.275, okay, 0.045, then 1.543, 0.42, 10.004, 3.943. One can see here there is a perfect joint compatibility 4.275, 4.275, okay, 0.45 this way, 0.45 this way, 0.284, 0.285, 943, 943 is a perfect joint compatibility in all the joints. See here. Let us also try to plot the end reaction of the whole system, which comes like this. So, we get the end values as 55.725 and 4.275, 0.045 and 0.045, which are exactly taken from here. Okay. Then 1.543, which is here, and 1.543, which is here, then 73.23, which is here, 4.356, which is here, okay. Then 2.82, which is here. Similarly, as far as this is concerned, 0.42, 5.374 and 3.807. The total load applied is actually 20 kilonewton per meter run for 3 meter 60. So, you can see here 55 and 4 makes it 60. Okay. So, the reaction is balanced and the moments are balanced. That is the final end reactions and moments. These are member reactions and moments. So, friends, we have discussed in this lecture an interesting space frame problem of 3D analysis. Okay. We also discussed the computer code to solve the problem. We have understood how the 3 dimension analysis becomes an extension of the concepts, the 2D analysis, we are able to arrive at the transformation matrix, we are able to arrive at the rotation matrix, we are able to arrive at the psi value easily for a given problem for any transformation chosen for the given problem. Friends, I want you to do more problems using this computer program and try to compare the results and enjoy how a 3-dimensional analysis using computer codes and hand calculations can be very simple and extended concept of 2D analysis. Thank you very much.